Hello again. We are going to find eigenvalues and eigenvectors of the given matrix. We use this characteristic equation determinant a minus lambda I is equal to 0, which means that 1 minus lambda 1 minus 2 4 minus lambda 4 1 minus 1 4 minus lambda is equal to 0 if and only if 1 minus lambda minus lambda minus 1 4 minus lambda minus 4 minus lambda minus 2 times 1 minus lambda minus 1 is equal to 0. Then 1 minus lambda times minus 4 lambda plus lambda squared, and this should be also plus minus 16 minus 4 lambda minus 4 minus 2 times minus 4 plus lambda is equal to 0. Let's open all parentheses here, lambda cube, and it is minus lambda cube, and plus 4 lambda squared and minus 4 lambda, and plus lambda squared minus 4 lambda plus 4 plus 4 lambda minus 12 plus 8 minus 2 lambda is equal to 0. We have minus lambda cube plus 5 lambda squared, and let's see the others. First of all, they are cancelled, which is easy to see that. Also these are cancelled, and we have minus 6 lambda is equal to 0. If we take minus lambda parenthesis here, the common parenthesis, we have lambda square minus 5 lambda plus 6 is equal to 0, and also this implies that lambda times lambda minus 2 times lambda minus 3, which is equal to 0. So it is easy to see that lambda 1 is equal to 0, lambda 2 is 2, and lambda 3 is equal to 3. They are all eigenvalues of A. And let me give you a hint. Since they are distinct and real numbers, we can easily say that the given matrix is diagonalizable. This is a theorem. So let's try to find all corresponding eigenvectors. So let alpha be an eigenvector corresponding to the lambda is equal to 0. Then a minus lambda 1I times alpha is equal to 0, which implies that since lambda 1 is equal to 0, we have alpha 1 plus alpha 2 minus 2 alpha 3 is equal to 0. Second equation, 4 alpha 1 plus 4 alpha 3 is equal to 0. Alpha 1 minus alpha 2 plus 4 alpha 3 is equal to 0. We have this equations, and in the second equation we obtain alpha 1 is equal to minus alpha 3, and we need to use another relation which is related to the about alpha 2. Let's put in the first matrix, first equation, instead of alpha 1 minus alpha 3. So this implies that alpha 2 is equal to 3 alpha 3. So we have alpha 1, alpha 2, alpha 3. Instead of alpha 1 we can write alpha 3, 3 alpha 3 and alpha 3, or alpha 3 times minus 1, 3, 1. Therefore the corresponding eigenvector to the eigenvalue lambda 1 is minus 1, 3 and 1. This is our first eigenvector. Now let beta is equal to beta 1, beta 2, beta 3 be an eigenvector corresponding to lambda 2 is equal to 2. So we have this equation. This means that minus beta 1 plus beta 2 minus 2 beta 3 is equal to 0, because we put in the equation instead of lambda 2 is equal to 2, so we get the first one. And the second equation was 4 beta 1 minus 2 beta 2 plus 4 beta 3 is equal to 0. And last one is beta 1 minus beta 2 plus 4. Oh, I'm sorry, it is not 4, because we subtract 4 by 2. So we have 2 beta 3 is equal to 0. Actually, first and third equation are the same. It is minus parentheses, you see. These are the same. So we can write here, let me write the first one, beta 1, or let me write, first of all, I would like to multiply the first equation by 2, and I'm going to write first and the second equation. Minus 2 beta 1 plus 2 beta 2 minus 4 beta 3 is equal to 0. 4 beta 1 minus 2 beta 2 plus 4 beta 3 is equal to 0. This implies that add them out, these are cancelled, and we have 2 beta 1 is equal to 0, which means that beta 1 is equal to 0. Okay, if we substitute this result into the last equation, we have minus beta 2 plus 2 beta 3 is equal to 0, or beta 2 is equal to 2 beta 3. Now we can use this relation. You know that our vector beta was beta 1, beta 2 and beta 3. So the first component is 0, beta 1. And instead of beta 2 we can write 2 beta 3. Also this is beta 3. Now we can put this out, 0, 2, 1. Therefore the second eigenvector of the given matrix is 0, 2, 1. This is eigenvector corresponding to lambda 2. Finally, let gamma is equal to gamma 1, gamma 2 and gamma 3 be corresponding eigenvector to lambda 3 is equal to 3. Then a minus lambda 3 times I times gamma is equal to 0 vector. It implies that minus 2 gamma 1 plus gamma 2 minus 2 gamma 3 is equal to 0. 4 gamma 1 minus 3 gamma 2 plus 4 gamma 3 is equal to 0. Gamma 1 minus gamma 2 plus gamma 3 is equal to 0. Okay, it seems to be they are all different equations, so let's take first and third one first of all. If we add them, they cancelled. Minus gamma 1 minus gamma 3 is equal to 0. So gamma 1 is equal to minus gamma 3. If we use this relation into the other, which is the second equation, this implies that 4 minus 4 gamma 3 minus 3 gamma 2 plus 4 gamma 0, so they are cancelled. It implies that gamma 2 is equal to 0. It should be gamma 2. Here I made a mistake. So yes, gamma 2 is this one. Therefore, gamma is now minus gamma 3, 0 and gamma 3. Finally, we have this eigenvector. Gamma lambda 3 is equal to minus 1, 0, 1. This is our eigenvector. And finally, as a conclusion, we have three different distinct real eigenvalues, and we obtain linearly independent three eigenvectors, so that is the given matrix is diagonalizable. Thank you for watching this video.